Let's get some more practice building lists recursively. And before we get into it, let's review some of the rules we've learned about recursive functions so far in the context of processing lists. First, we always need some base case in a recursive process, something that's going to stop the recursion and prevent it from being infinite. And when we're working with lists, we tend to need to be aware of when is a list empty, such that we don't try and process an empty list in a way that would cause our program to error. When we're recurring, we always need to be changing something, and typically this is an argument that brings us closer to our base case, right? So when we recur on a list, we'll tend to recur on the rest of the list. And one of the rules we learned in the most recent lecture is if we're trying to build a list recursively, we want to process the first value of some input list and then cons that result onto repeating the same process applied recursively to the rest of the list, right? And so this last rule tends to be the one that is the most difficult to become comfortable with. And it's pretty dense, right? This is a mouthful of a sentence. So what I want to do is change context and think about perhaps a real world example of this, right? So imagine you're the owner of the hottest club in Chapel Hill. Now, I don't know if that's like Ma or if that's the library or He's Not. I guess He's Not's not really a club, but let's say it's Top of Lenore. Yeah, that's right. Not Top of the Hill. Top of Lenore is having a DJ night 21 and up, right? And we need to give the folks that check flex or that check your meal plans some instructions. They're going to be our bouncers as to who to let in to Top of Lenore for the most dank waffles you can imagine building yourself, right? So what are the recursive instructions you would give to the bouncer of a club? Well, we can imagine an algorithm that looks something like this. If the entrance to the line is empty, your job is done, right? If there's no one waiting in line, there's no work for you to do. You can chill, your job is done. Otherwise, if there is a line, focus your efforts entirely on the person at the front of the line. And if they are 21 or over, then you can cons them to the bar line, going up the escalator into Top Lenore, right? And then repeat the same process on the rest of the line. If that person is not 21, no matter what they say to you, send them somewhere else, right? Send them to Rams. I don't know. Repeat this process on the rest of the line. All right? So we need to process the whole line, whether or not someone is 21 or under. Either of those cases, we still need to continue processing the rest of the line. It's not like the first person who's not 21, we're going to stop letting anyone else in after that. So we're going to apply this process recursively to the rest of the line no matter what. But the key distinction here is in the first case that we are letting people in, you will notice that there's a condition, and there's a condition that says if the person is 21 or over, then what you're going to do is cons them on to the bar line. All right. So what I want you to do is open up today's lecture materials, the O1 bouncer app example, and let's take a look at where our starting point is here. All right. So we've got some ages here. We've got some ages that are 18, 21, 16, 83. I don't know who the 83-year-old is that's trying to get into Top of Lenore's DJ night, but we should tell them that it's not safe with COVID going around, and 22, right? And so when we print those ages, we see them in this format. And notice this is one of the formats that we can visualize a list in, just as a sequence of numbers that ends in null. And we have implicit arrows that we could imagine connecting those nodes together. Now, your goal then is to implement this bouncer algorithm, and bouncer is given a list. We've already handled the base case for you. So if the list is empty, then your job is done. And in the else, we've already taken the first value from that list and assigned it to the variable age. So your goal is to implement the recursive list building logic here that would implement a bouncer's algorithm, right? So pause the video here, try and implement this logic on your own, and continue once you've got the subsequent list of ages that's printing that will only be those values that are 21 or over. All right, so let's try implementing this together and talking through the same series of thoughts that you had as you were implementing this. So we need a conditional here. We need an if statement that asks if age is greater than or equal to 21. This will be the case where what we're going to do is say, okay, we're going to build up a new list of people, or a new list of ages in this case, that are those that we're admitting into our bar. Right? So we're going to return, and then that statement that's a mouthful is we're going to cons the first value that we just processed. So age is the value that we're processing onto applying the same algorithm, the same bouncer algorithm to the rest of the list, right? And so the idea here is we're saying, okay, if you are 21 or over, we're going to cons that age onto the same process applied to the rest of the list. So this will be the bouncer moving through the rest of the list. Now, in the other case where you are less than, the age is less than 21, right? What are we going to do? Well, we could return null here, right? But if we return null here, as soon as we reach a non-21, a value that's less than 21, this process completes and our job is done, right? So maybe if I had one more person at the front of this line that was, say, 22, and I save that, notice we get 22 and then null because this process is done. But what we really wanted to do was say, we're just going to skip over this age. We're not going to cons that age onto the result, right? We're not going to include that age in the returned list of ages. We're just going to say, okay, you can go to Rams. We're going to bounce the rest of the list, right? And we're going to return the result of bouncing the rest of the list. And so you notice here, we have now 21, 22, 21, this wild 83 value, and then 22, right? And so the values 18, 16, and if I were to include one more, like say 20, which was right on the cusp, are getting filtered out of the returned result here. So if we wanted to try and visualize what's happening, let's imagine this input list, right? So if we imagine this bouncer algorithm being applied to this particular node whose value is 22, we know that the result is going to be return cons of age onto the rest of the list. So that's going to return cons of 22 onto the bouncer applied to the rest of the list, right? Well, what is the bouncer applied to the rest of the list? Well, if we think about what is 18 going to return, well, notice that 18 is going to return just bounce the rest of the list. We're not actually consing any new values or constructing any new part of a list here. We're saying continue on, ignore that. And when we get to the 21 case, we know that 21 is going to return cons of 21 onto the same bouncer algorithm applied to the rest of the list. 16 we're going to skip over. With 83, we're going to return cons of 83 onto the result of applying this process to the rest of the list. When we test for 20, we know that we're just going to return the result of applying this process, so I'm not even going to illustrate it here. When we get to 22, we know that we're going to return cons of 22 onto this process applied to the rest of this list. And the rest of the list is now null, right? And so when we get to this point, we're just going to fill in null. And we had one parenthesis there. We had one parenthesis to finish the 83 call, one for here, one for here. Like this would be the sequence of cons values that get evaluated. And as we move our way back up, ultimately we would have a list that goes 22 to 21 to 83 to 22 again, and then to null, right? And so thinking through this recursive process, the key thing that's being illustrated here versus anything we saw before in acronymify is we are choosing whether or not to include some value in our output list or the result of this algorithm based on whether or not we cons some value to the result or we just skip over it, right? And so this is a common strategy when we're trying to filter some input list down to some resulting list based on some specific criteria, in this case, whether or not the age was greater than or equal to 21. So coming back to our rules of recursion, what we just emphasized was this rule number 3. When we build a list, process the first value, cons it onto the rest of the list, processed by that same recursive algorithm. And what I want to do next is bring together 2 different forms of recursion we've looked at. Right? So we've looked at recursion most recently when we're processing a list. In our base cases, when the list is empty, and when we're processing a list, we tend to need to recur on the rest of the list, so we're making progress through it one by one, right? And when we're recurring with numbers, we test generally whether some number is out of bounds. So if we're testing with a number parameter that's the value we're recurring on, we would use some bounds case, like maybe is the number still greater than 0 or is the number less than 10, whatever our bounds is. And then when we're making those recursive function calls, we are using some arithmetic on that particular parameter to bring us closer to the base case, right? And what I want to do in this next example is give you an opportunity to bring these 2 ideas together. We're going to our recursive steps are going to use numbers, but what we're going to be producing in the process is actually a list. So we're going to sort of mix these 2 modalities of thinking. We're going to recur using numbers as our parameters while building up and returning a list as the resulting output. So the next example is going to be working on a function named range. And the purpose of this function is shown in this example call, right? So here we have range where we're giving arguments 2 and 5. So we're saying, this range function, I want you to build up a list of values that range between 2 and 5 inclusive, right? So that would return a list where 2 is followed by 3, is followed by 4, is followed by 5, is followed by null, right? So one of the key questions to consider is, what is the base case in this example? What is the simplest case we can imagine after the base case? And what is the first element you're consing onto this recursive process applied at each step? Right? So these are the 3 key questions to think about. And sadly, of course, we're not going to be actually checking in on poll everywhere, but there are questions on Gradescope to respond to relative to this once you've got a working implementation. So let's talk through some of these questions at a conceptual level. What is the base case? So this would be, when do we stop making forward progress? Well, remember, when we're recurring with numbers, the rule is we need some test condition to know when we stop recurring. And in this case, if we're trying to produce a range, it's probably when these numbers are equal to one another, right? So when the range is from 5 to 5, so when we have a function call like range from 5 to 5, then what we're going to do is return 5 followed by null, right? So this would be our base case. Next, we're going to think about, well, what is the simplest case you can imagine after the base case? Okay, well, maybe we think about a range call from 4 to 5, right? So range from 4 to 5, and that would result. Let me actually use a double arrow here to indicate this is the return value. The return value would be 4 followed by 5 followed by null, right? And the idea here that's useful when we're trying to design recursive functions is we're really trying to look at what is the difference between what our base case does and then the next case that is very near to it, right? So rather than thinking about 3 to 5, which would be 2 steps away, we're trying to think about what is the simplest step away from our base case that we can imagine moving from one case to the next in a single recursive step. And when we do that, that gives us a sense of what it is that we need to change in order to move us closer to the base case. So notice what changed about these arguments relative to our base case arguments is that we are incrementing our first argument by 1, right? So it took +1 in just the first argument position. We kept the second argument position exactly the same, right? So in this next question is, what is the first element you're consing onto the natural recursion of each step, right? And so this is the question that will help us figure out what is it that we need to be focused on in order to build up our resulting list. And we can figure that out by comparing these two things, right? So if our initial list at our base case in this example call was just 5 followed by null, well, the only thing that really changed is we consed 4 onto 5 followed by null. So this is our recursively built up list. So now the question here is, what is the first element we're consing onto that? Well, the first element is going to be our first parameter, right? So the first value that we give to it as an argument, which becomes inside of that function the first parameter. Right? So 4 in this case is what's going to be consed onto range applied to the values 5 and 5, right? So when we apply this process recursively and move closer to the base case, we would move from range 4 to 5 to range 5 to 5. Right? So let's try actually implementing this, these concepts in code. Right? So I'm going to switch over to VS Code, and here we go. Let's see. All right, so I'm going to clear these notes, but we're going to actually, before I clear these notes, okay, so we are in VS Code, and now what we need to do is design our function here. So range, we need to be sure we handle the base case. And that was when from is equal to 2, right? So in our example, we had from range from 5 to 5. And the condition that we would actually be able to specify using any parameters would be from is equal to 2. And then the recursive case was to increase from by 1 and cons from onto range of from +1 to, right? So let's try and actually get this into code, and then we'll talk through this intuition here, right? So the base case, when we handle the case of from is equal to 2, we want to add the if statement. If from parameter is equal to the 2 parameter, then what we're going to do is this is, we could add an example here. Example is from 5 to 5. What we expect back is a list where 5 is followed by null, right? So if we want to return that, we could return cons of 5 onto null, right? And we don't want 5 here specifically, we want from, right? And in the recursive case, what we can do is I'm going to move my comments into this block. And let me move these comments into this block, okay? So in the recursive case, we know what we typically do is process the first value, right? So what is the first value? So and I might name this value be from, right? So our focus is what is the current value of from, right? And in the case where the example was from 4 to 5, range of 4 to 5, and I accidentally miswrote the name of that function here. That should have been range of 5 to 5, right? So in this example function call range from 4 to 5, the from value is 4, right? And so the value that we're processing, that's going to be the start of the new list that we're building up, is going to be stored in this variable named value. I didn't need to set up this variable. In fact, it's a little bit redundant because from is already a parameter who has that value in it. But if we needed to apply any computation here, it's usually helpful to do this in its own variable. Right? And what we're going to do is return consing of the first value that we want to add to the list we're building up recursively onto the same process that we're applying to the rest of the problem we're trying to solve, move us closer to the base case. So what brings us closer to the base case? Well, again, remember, if we imagine that if we're one step away when range arguments are 4 and 5, and to get us to a base case, we would need to have from 5 to 5. What we're going to do is say, okay, the range is going to be the current value from +1. So we're increasing our from argument to be closer to the value we're recurring towards, all right? And so in this case, we're leaving 2 the same, but we're still getting closer and closer to our base case when we are increasing the from parameter by 1 as the call happens recursively, all right? So I need to change my example here, to range. And when I save this, notice that the example call was 2 and 9, but let's actually use those examples we just showed off in the previous slide and that we've been thinking about. So when we call range from 5 to 5, notice we are just going, from is equal to 2, so we would return the cons of from, which was 5, onto null, which gives us just the list where 5 is followed by null. But if we tried from 4 to 5, we get back the list that we would expect, and the first call to this function would hit the else branch, right? Because from is not equal to 2, 4 is not equal to 5. So what we would do is we would cons 4 onto the same range process, but we're moving closer to our base case by increasing the from argument by 1 and keeping the to argument the same, right? And this winds up working even if we had, say, like 0 to 5, so on and so forth, right? But can you imagine a case where this is a little bit naive, where we would still have potentially infinite recursion? What if we wanted the range from 10 to 5? So 10, 9, 8, 7, 6, 5, 6, 5. Uh-oh. Well, what happens here? Well, we have infinite recursion. We see a stack overflow. And where's that coming from? Well, if we were increasing our from parameter by 1 until it's equal to 2, we're going to have calls to the range function that are recursive, that are 10, 11, 12, 13, 14. And we're not getting closer to 5, which is our stopping condition, right? So I want you to try extending this function and adding another recursive case to handle a varying, the other way that we can imagine using this function, which is our first argument is going to be larger than our second, right? So we can make a range from a larger number to a smaller number, and that will give us a list of numbers in decreasing order, right? So pause the video here and try responding to this hands-on in code, and then filling out the responses to questions in Gradescope. All right, well, let's try working through this together. So we've got the case in our code currently where this will work as long as from is less than 2, right? So maybe what we do here is we say, okay, if from is less than 2, that's when we'll return cons of the value followed by this range algorithm applied to the arguments where from is increased by 1 and 2 remains the same. Otherwise, we want to return the cons of this first value. And what are we going to cons that onto? Well, the range of from -1 to 2, right? So the intuition here is if from is less than 2, we need to increase from to bring it closer to the parameter that tells us when to stop, right? So in the case where we start from 0 and we go from 0 to 5, 0 being the from parameter value initially and 5 being the to parameter value initially. In this case, where from is less than 2, we would increase from by 1. So 0 would go to 1, 2, 3, 4, 5. And then once we hit 5, range of 5 and 5, that's when we hit our base case, right? That just returns to us 5 followed by the empty list. Now, if from is greater than 2, what we would do is go to the else branch. And if from is greater than 2, we're not going to add 1 to the next recursive call. We're going to subtract 1, and that's going to bring us closer to our ending position. So now if we start from 10, right, our first call to range would be from 10 to 5. And the second call to range would be subtract 1 from, so 9 to 5, 8 to 5, 7 to 5, 6 to 5, 5 to 5. And once we hit that base case, that's when we would stop recurring. Now, if I wanted to clean this up just a little bit, as I mentioned to you, we don't really need to establish this value here, right? But if we wanted to do some computation here, like give me back the range of the numbers doubled here, we could apply some computation, and it would probably make sense to define a variable here that we could manipulate with some arithmetic. But because we're trying to just effectively build up values, and we already have the value that we want in our from parameter, we didn't really need to establish that value variable, right? And this has the exact same implementation, is a little bit cleaner, because every time we're returning some value, we're consing this first element onto, and then the question is, what is the list that we're consing it onto? Well, that's going to be in the case where from is equal to 2, the empty list, that's our base case. Otherwise, the same algorithmic process applied to the next closest step that brings us closer to the base case. So these are two recursive functions, and in this case, we were thinking about in the range function, how do we recur with number parameters, but ultimately build up a list of nodes? So we can mix these modalities if we'd like. And in the previous example, we looked at, well, what if we didn't actually want to have a one-to-one correspondence between our input list of ages and our output list of ages? So we filtered that list down by some criteria. And in both of these cases, we're looking at some creative ways to begin building up lists recursively. And hopefully you can start to appreciate that this range function, for example, we're very basically describing what happens at each given step. And then in the recursive call, that's where the rest of the details are left to be worked out, right? So in any function call, all we care about is what is the next thing we want to add to the front of our list. And then we're going to leave the problem of figuring out, well, what happens after that to the recursive step. Great work on these videos today. Recursion tends to be something that feels a little bit unnatural coming from iteration, but hopefully this is starting to feel a bit more comfortable today. And as a reminder, the review session is tonight at 4 p.m. Look on CourseCare for those details. Great work today.